Okay, the next thing we're going to take a look at is net ionic equations for single replacement reactions. The last one we looked at double replacement reactions. Single replacement reactions rely on some of the same things in terms of the solubility of compounds and those soluble compounds dissociating into their component ions. But there's a little difference with single replacement reactions because in a single replacement reaction, we have a general equation where A plus BC reacts to produce something. Okay, for every single replacement reaction, one compound, as long as it's more reactive, or sorry, one element, I should say, as long as it's more reactive, will kick out another one. So in this case, let's say A is a metal and BC is a compound made up of a metal, B being the metal, C the nonmetal. In a single replacement reaction, as long as A is more reactive than B, A is going to come in and take the place of B, and B kind of gets booted out. Okay, so the result of this would look like AC plus B, something along those lines. An actual example of this might be something like the following reaction, where we would have magnesium metal, and I can say it's magnesium metal by calling this solid. And let's take a solution of copper 2 nitrate, so CuNO3 2, and it's a solution, so aqueous. Hopefully we're already thinking in our heads, oh, that's an aqueous compound. It's going to dissociate into its ion. But in this case, magnesium is more reactive than copper. I'll show you where we can go find those rules. So magnesium will take the place of the copper, and we end up with magnesium nitrate in solution plus, the copper got booted out, or the copper was replaced. So I'm running out of room here. I'm going to have to sneak a solid in there. That's an S for solid. And our equation looks like this. Okay, now you might be already thinking that the copper nitrate over here and the magnesium nitrate over here are going to dissociate into their respective ions. Copper 2 plus ions and nitrate -1 ions on the reactant side, and magnesium 2 plus ions and nitrate 1 minus ions on the product side. Okay, well, if that's the case, then the nitrate ion didn't change from the reactant side to the product side. And the nitrate ion is a spectator. And just like in a double replacement reaction, we remove the spectators when we move to a net ionic equation. So I'm just going to cross these out to show what we're doing. But I would have magnesium, solid magnesium, so magnesium metal, and in this case, the copper 2 ions, so Cu 2 plus, that's in solution, so AQ, and this reacts to form magnesium ions, and copper metal. Okay, and in fact, we saw this reaction in our activity series lab, where the magnesium the magnesium replaced the copper. Magnesium is a relatively reactive metal. Copper is a relatively non-reactive metal. And we end up with this. Spectator ions have been removed, and we're left with our net ionic equation. The same pattern comes up over and over in these, in that we have a solid metal with no charge reacting with a metal ion in solution, a charged metal ion in solution. And on the product side, we end up with what was the metal on the reactant side is now the ion in solution. And what was the ion in solution on the reactant side is now the solid metal on the product side. is a very consistent pattern. We see this over and over and over again with single replacement reactions. I'm going to hop over. I did a little search before. You have a copy of this on the back of your periodic table, but we have our activity series, or this one says reactivity series of metals, with things like potassium, sodium, calcium. Potassium, sodium, calcium up towards the top being the most reactive. Things like gold, silver, mercury, copper down towards the bottom, those are less reactive. Hydrogen is in there as just a place to show where that would fall in terms of its relative reactivity. And that's an important point here, that these are all relative. There's no numbers or anything on this particular one. Okay, but there are hundreds, or if not thousands or millions, of activity series charts that you can find by doing a simple Google search. The one that's on the back of your periodic table is good enough for what we need in intro-level chemistry. So you can always refer to that one. Okay, where this comes back to, and if I hop back here, we may run into a situation where we have kind of a similar looking reaction, where it would be copper, solid copper, reacting with magnesium nitrate. Okay, in solution. And in this case, in order to predict the products, we need to look at what is more reactive. And I come back over here and I look, magnesium is more reactive than copper, or copper is less reactive than magnesium. Maybe that's a more useful way of doing that. And if copper is less reactive, it's not going to come in here and kick our magnesium out. This doesn't happen. So in this case, and we saw this in our lab as well, we would have no reaction here. Okay, so a couple of things. We can always check our activity series to determine if a reaction will take place. In order for that reaction to take place, a more reactive metal will replace the other one. And we can also write our net ionic equations. Okay, the net ionic equation is always going to remove the spectator ion. And the one we looked at up here, that was the nitrate, was the spectator. Okay. Hope this helps. Please let me know if you have any questions. And we'll talk. Before I check out here, sometimes, like, I looked at it from the metal standpoint, a metal replacing a metal. In other words, an A replacing a B. But if A was being played by a non-metal here, the non-metal would not replace a metal. The non-metal would be more likely to replace the non-metal. Okay, and there's an activity series for non-metals on the back of your periodic table as well. The same rules apply. We just need to be a little careful if it's a metal or a non-metal. Okay, I mean it now. I think that's all that I have. Okay, let me know if you have any questions.